On the first day of this unit, we said that there were 4 properties of waves that were exhibited by EMR. Diffraction, the spreading out of a wave; interference, when one wave combines with another; polarization, where we filter out a wave; and the fourth one was refraction, the bending of a wave. The picture you see up on the board right now is of a pencil and water. It looks like the pencil is bent. It's not really. We're just tricked into thinking it's bent because the light that bounces off of the pencil inside the water refracts or changes direction. It bends when it goes from the water to the air. It tricks our brains into thinking the pencil is in a place where it's not really, right? That pencil right here is really straight right here. It's just playing mind games on us. It's tricking us because of the bending of the light when it goes from water to air. We define refraction as the bending of a wave. We said that refraction takes place because of a change in speed of a wave. I want to show you right now an analogy to help you to understand how a wave changing speed can lead to a change in direction. Let's say we've got 2 materials here: pavement, a parking lot, and a swamp. Maybe there's a half a meter of water in the swamp. It's easy to walk in the parking lot. It's harder, much harder, to walk in the swamp. Let's say that for whatever reason, there's a bunch of soldiers lined up here in the parking lot. And if we look at these soldiers from above, maybe we're in a helicopter hovering above them, or maybe we're in a high building looking down at these soldiers, it looks at a distance as if they form a straight line. It's a wave front, or at least it represents a wave front. Now, soldiers all march in stride. So 2 seconds later, or 2 seconds after this moment, soldier number 1 is up here. Soldier number 2 marches in stride with him or her, so soldier number 2 is up here right beside soldier number 1. Number 3, number 4, number 5, number 6. What happens to soldier number 7? He's in the water now, in the swamp, so he's falling behind. He's slowing down a little bit, so soldier number 7 is in this position. If, again, we're looking at this group of soldiers from above, then it looks like a wave front that looks like this. Now, let's fast forward 2 more seconds into the future. Soldier 1, 2, 3, 4, soldier 5. Soldier 6 is now in the swamp and slows down as a result of that. Soldier 7 still in the swamp. From that balcony, 20 stories up, it looks like a wave front that looks like this. 2 more seconds in the future. Now soldier number 4 has entered the water. Soldier number 5 is in the water. Soldier number 6 is in the water. And 7 is in the water. Looks something like this. If this soldiers marching represents a wave, then the wave was traveling this way when it was in the parking lot. But as the wave entered a new medium and changed speed, slowed down, the wave changed direction. Now the wave is going this way. So the change in speed led to a change in direction. And it also led to a change in something else. Anybody want to take a stab at what else changes as a result of the change in speed? Look at the diagram here. It's staring you right in the face. It's not easy, but it's staring you right in the face. What is it, Ben? The wavelength. Yeah. Look at this wavelength right here. It's a certain value, whatever it is, the distance between crest and crest. And look at it over here. It's much smaller. So the change in speed led us to a change in direction, and it also led us to a change in wavelength. What doesn't change? Yeah. We learned that in Physics 20, right? Once a wave is made, the frequency never changes. We had 1, 2, 3, 4 waves in 8 seconds. Here we have 1, 2, 3, 4 waves in 8 seconds. The frequency of the wave remains the same. Refraction is the bending of a wave, and it occurs due to the change in speed of the wave. As a result of the change in speed, the direction changes, and the wavelength also changes. That's refraction. Right? That's what we defined refraction as. Now you understand maybe a little bit more why refraction takes place. The bending of a wave, when the wave passes from one medium to another, and it happens because of the change in speed in the wave. Now, in order to quantify refraction, the amount of bending that takes place when a wave goes from one medium or one material to another, we got to define a term. It's called the Index of Refraction. This is a term that you might have heard your eye doctor talk about, although he or she probably called it just index, as opposed to index of refraction. But that's what it means. The index of refraction we think of in everyday thinking as how much light bends when it goes from one medium to another. The higher the index, the more light bends. But we technically define it as a ratio of the speed of light in a vacuum to the speed of light in whatever medium it is that you're trying to find the index of refraction. The higher the index of refraction, the more light bends. When you go to your eye doctor and the eye doctor says you need glasses, would you like regular index lenses or high index lenses? You say, what's the difference? Your eye doctor says, well, the high index lenses can be thinner. Why can the high index lenses be thinner? It's because they bend light more. If I have a problem with my eyes that I need light to bend before it goes into my eyes, the higher the index of refraction of the lenses, the thinner the lenses can be and still cause the same amount of bending. The higher the index of refraction, the more light bends when it goes into and then out of that glass. The symbol for the index of refraction is n. It's a lowercase n. The equation for the index of refraction is going to be, it's a ratio. What did we say the other day ratio means? Comparison, yes. Ratio, compare, or divide. We're going to divide the speed of light in a vacuum, which is c, or 3.00 times 10 to the 8 meters per second, by v. So we'll say the speed of light in medium 1, the index of refraction of medium 1 is equal to c divided by the speed of light in medium 1. This v, by the way, will always be less than or equal to 3.00 times 10 to the 8. It'll never be bigger. The bottom number will never be bigger than the top, which means the index of refraction will always be greater or equal to what? 1. The index of refraction of air is like 1.003 or something like that. It's really, really close to 1. Light doesn't bend very much in air. The index of refraction of water is about 1.3. Light bends more in water than it does in air. For glass, it's about 1.5. It bends more in glass than it does in air. For diamond, it's about 2.4. Light bends way more in diamond than it does in glass, and that's why diamond sparkles so much compared to glass, because it has such a high index of refraction. What are the units here? What are the units for index of refraction? C over V. Speed of light divided by the speed of light in the medium. Meters per second over meters per second, which cancels, which means there are no units. We say it's a dimensionless quantity. There are no units associated with it. Now, I'm going to draw a picture of a prism, a triangular prism. I mean, we get all kinds of different shapes of prisms, right? Triangle prism, rectangular prism, cylindrical prism, anything that's three-dimensional, basically. We're going to shine a ray of red light into that prism. That ray of red light will change speed when it enters the prism. And as a result of that change in speed, it will change direction. And then when it leaves the prism, it will change speed and therefore direction again. And it looks something like this. Let's shine a ray of blue light through that prism now. Superimpose it over top of the red light. It's taking the same path. When the blue light enters the prism, it will also change speed and also change direction, but a different amount than the red light. Here's the reason. The index of refraction for glass for red is slightly less than the index of refraction for glass for blue. Glass and plastic and any other material has a slightly different index of refraction for each different frequency. The higher the frequency, the greater the index of refraction and the more bending of light will take place. If I shone white light through this, which consists of all the colors of the rainbow, that's the dark side of the moon poster that we have over there, right? When white light goes through, then you're going to find that red light refracts the least, violet light refracts the most, and all the other colors refract in between. It ends up splitting the light up into a rainbow. That phenomenon where we split up the light because of refraction in different amounts, because of a difference in index of refraction, is called dispersion. I'll give you some formal notes on dispersion tomorrow. Just understand what it means right now, and then tomorrow we'll formalize it a little bit. But before we call it a day, I want to show you an application of dispersion beyond splitting light up into its colors. Every once in a while, right? You're walking somewhere and you see, in my kitchen, I notice this a lot because of the panes of glass in the door that goes out to my backyard. There's beveled panes of glass. When light comes through it at the right angle, I see this spectrum of light, red, orange, yellow, green, blue, indigo, and violet on my table. Every once in a while you see that, right? It's kind of neat, but there's other applications of it as well beyond a literal prism like that. Let me show you one of them before we pack it up. Here's the Earth. There's a guy standing on the top of the Earth right here. There's another person standing on this location on the Earth. Here's the sun. Clearly this isn't drawn to scale. The sun is, what, 1,000 times bigger than the Earth? 1,000 Earths will fit inside the sun, something like that. The sun is way bigger, but good enough. The Earth has an atmosphere surrounding it, and that atmosphere changes. Sometimes it always contains a lot of nitrogen, oxygen. Sometimes certain spots, certain locations contain a lot of moisture, sometimes not so much. Sometimes it contains a lot of dust, sometimes not so much. But there's always an atmosphere surrounding it, and that atmosphere can act as a prism. When white light comes from the sun toward the Earth, it encounters that prism that is our atmosphere. Red light will refract and bend because of a change in speed of red light when it enters the atmosphere. But the atmosphere has a slightly different index of refraction for red light as it does other colors. So other colors will refract differently than red light. Red light refracts the least because the index of refraction is the lowest. Violet light, bluish violet light, refracts the most because the atmosphere has the highest index of refraction for those colors. Forget about the colors there for a second. Take a look at person number one. Person number one. What time of day is it based on the position of the sun for person number one? Where is the sun relative to that person number one? The sun is almost ready to... Go ahead. Yeah, not west, east, but could be west, could be east. The sun is either ready to rise or set, right? The sun is low on the horizon. What color is the sky sometimes when the sun is rising and setting? Red. Red, because red light refracts less than other colors. What time of day is it for person number two? Where's the sun? Forget about the light here for a second. Where's the sun? Right above. What time of day is it? Daytime. Probably noontime, 1 o'clock, 2 o'clock. What color is the sky? Blue. Red light refracts less than blue light. That's why at sunrise and sunset, you often see red, but during the middle of the day, you see more bluish because of dispersion.